Okay, welcome everybody to this second workshop on analysis of variance. Previously, in the first workshop, we looked at how we use the AFEX package for one-way analysis of variance for between participants designs and also for repeated measures designs. When we find that we have a significant effect in our data and we've got more than two experimental conditions, we examined how to use the EM means function in the EM means package for running up follow-up tests to actually determine what levels of a factor differ from what other levels. And we also discussed a number of issues around the need to correct for multiple comparisons to avoid the family-wise error problem. The final video in that previous workshop, we looked at how to build models for factorial analysis of variance, and again how to interpret the output of those models using the EM means function, though in this case I think we focus more on how to interpret interaction effects. So we're going to sort of move on a little bit now to analysis of covariance or ANOVA. And you can kind of think of ANOVA as a mix of ANOVA and regression. Both are, they're actually the same thing. So ANOVA and regression are actually both the general linear model at their core. And later on in this video, I'm going to demonstrate and show how we can actually model, we can actually build ANOVA as a special case of regression. Because these things are all actually the same under the hood. Although I suspect that when they're taught at undergraduate level, they're in most cases taught as if they're quite separate things, but they're not. They're actually all examples of the general linear model. So we're going to focus on ANOVA initially. This is where we are interested in controlling for the effect of an additional variable that we've maybe measured. So let's think about one of our early examples where we had, we were looking at sort of, was it caffeine consumption on performance on a motor task, and we had, it was a between participants design, and we had three groups of participants, a double espresso group, a group that drank single espresso, and then a third group that drank just water. So these were our three groups. This was our independent variable, the type of beverage they drank. And motor performance was our dependent variable. So that was kind of what we looked at previously. So imagine we're kind of doing this sort of thing again. And imagine we sample from a new group of participants. And we think that actually another thing that might be quite useful to measure in terms of factors or variables that affect motor performance is maybe how often people play computer games. Because we might be thinking, some people play a lot of computer games and they just maybe better have sort of motor skills than people who don't. So we're collecting, we're doing this new experiment where we also measure people's time spent playing computer games as well as manipulating our independent variable. And what we want to do in this case is we want to see the effect on our dependent variable of motor ability. So the effect on our dependent variable of our experimental manipulation, which is our independent variable, after we have removed the influence of computer game playing frequency, which is our covariate in this case. So imagine we've got a good measure of computer games frequency, and it might be something like number of hours that people play per week on computer games. So we've maybe collected these data using some sort of diary recording method, but we've got the measure, we've got the data. So in addition to manipulating the type of beverage that we give people, whether it's double espresso, single espresso, or water, we've also got this measure of how often they play computer games. Okay. So first of all, let's look to see what the relationship might be between our covariate, which is the number of hours per week they spend playing computer games. So we're going to call this gaming frequency. So the relationship between our covariate of gaming frequency and our dependent variable of motor ability. So let's do a little visualization. We're also going to cluster, or at least represent using different colors, our three different experimental groups. So if we ignore the colors just to begin with, we can see that the relationship between our dependent variable on the y-axis of motor ability and our covariate of gaming frequency. So if you were to draw a regression line, you draw it basically up from bottom left to top right through that. So we can immediately see that there seems to be a strong relationship between people's performance on our motor task, our dependent variable, and the number of hours they spend per week playing computer games. And interestingly, for just random reasons, we also see that our gaming ability groups appear to be clustering in our data by condition. Okay, so we have our double espresso people up here who tend to be also people who do a lot of computer games, and our water group down here who tend to be people who really don't play many computer games at all. So immediately you might think that the influence of our experimental manipulation on motor ability is going to be influenced by this extra covariate that we've measured. So first of all, let's ignore the covariate and see what we've got. So we're going to build an analysis of variance model using the AOV4 function, ignoring the covariate. So this is a basic between participants design effectively that we're going to first model. So we're going to say that ability, which is our dependent variable, is predicted by condition, which is our independent variable, plus we've got this random effect of participant. So this is no different to what we did in the second video in the previous workshop. And then we can ask for an output of that model, and we see that according to this model, we've got a significant F value, a minuscule P value. So on the basis of this, we might then follow the model up with some pairwise comparisons. And that would seem like a reasonable thing to do. So we'll run our pairwise comparisons and we get the estimated marginal means. We see that our double espresso group has got the best performance on our measure. The motor task ability is 9.02. Our water group is 4.82 and our single espresso group is somewhere in the middle. And then we ask for all of our pairwise comparisons and we get cheeky corrected pairwise comparisons, and we see they're all significant from each other. So we might conclude on this basis that we have a significant effective condition and that each of our three groups differs from each of our other groups, with the double espresso group scoring highest on the task, the single espresso group scoring the next highest, and our water group scoring the lowest. Okay, so if we ignored the covariate, we'd arrive at this conclusion. But now let's control for the effect of our covariate. So let's actually build a model which includes the covariate that we've actually measured. And we do it in a very similar sort of way. AOV4, where ability is predicted, we're going to put our covariate in first now. So our motor ability is predicted by gaming frequency, that's on the continuous scale, plus our experimental condition, plus our random effect. And we're going to say factorize is equal to false because we don't want this covariate to be factorized because it's not a factor, it's a continuous variable. So we're going to build this model, which now has gaming frequency added. I'm going to map it onto a variable I'm calling model ANOVA. And I ask for a model ANOVA output, and we see now that the effective condition that previously was 53.432 is now less than 1. So the effective condition is no longer present. And actually, the effective gaming frequency is significant. The F value associated with that is 53.56. So what this basically means is that a lot of the variance that we previously attributed to our experimental condition manipulation can actually be better explained by our covariate of gaming frequency. So by building this ANOVA model, we actually see that when we control for the effect of our covariate, we actually have no effect of our experimental manipulation. We can ask for output of this model using the means function again. So we're not interested in pairwise comparison in this case. What we're actually interested in are the estimated marginal means, which are the adjusted means that are calculated by taking into consideration the influence of our covariate for each of our three experimental groups. So when we run the means function, we actually get, in the first bit of the output, the estimated marginal means. So these are the adjusted means taking account of the fact of the influence of our covariate. And we actually see that the double espresso estimated marginal mean, the adjusted mean, is 6.32, which contrasts with the unadjusted mean, which was 9.02. The single espresso adjusted mean is 6.87, which contrasts with the unadjusted mean, which was 6.69. And finally, the water group, the adjusted mean, taking on board the influence of our covariate, is 7.33, whereas the unadjusted mean, sort of the raw descriptive, was 4.82. So perhaps now it's not remotely surprising that there's no difference between these three conditions, because by looking at the adjusted means, we can kind of see they're roughly equivalent to each other. So the ANOVA model operates over these adjusted means, which were adjusted on the basis of the presence of the covariate in our model. So this is something I've touched on previously about why we shouldn't use the AOV function in base R, in other words, the function that's built into R as it comes. If we had used the AOV function that's built into base R, that would have worked by conducting what are known as type 1 or sequential sums of squares. We need to use the AOV4 function in the AFX package for what's known as type 3 sums of squares. And the difference between these different ways of calculating the sums of squares is actually quite important. So for type 1 sums of squares, they're calculated sequentially. So first for the main effective factor A, then for the main effective factor B, and then for the interaction between the two. And the order in which they're calculated matters. So the order in which you put the terms into your ANOVA model actually matters, because that will change the way in which the sums of squares are calculated. And this can actually be quite misleading because it's sensitive to order, but also can be problematic for unbalanced designs or cases where your predictors are actually correlated with each other. So you want to avoid, generally speaking, type 1 sums of squares for the sorts of experimental designs that we will be building in the context of psychology and biomedical and life sciences generally as well. Type 2 sums of squares assumes that the presence of no interaction effect when testing main effects, or higher order interactions when testing for lower order interactions. And sometimes you'll see people report type 2 sums of squares. But generally speaking, most commonly used by a long way are type 3 sums of squares, because they adjust for the effects in the presence of other effects and are actually calculated independently of the order of terms as the order specified in your model. And if you speak to a statistician about this, and I'm obviously not a statistician, but if you speak to a statistician about this, you'll actually realize there's quite a lot of debate about which one is technically correct. In a sense, each has got its own purpose. But for the sorts of factorial designs that we are interested in building and understanding, where really the main story is going to be in the sort of interactions that we have, type 3 sums of squares will tend to be the ones that are most commonly used and reported, which is one reason why the AOV4 function in the AFX package uses the type 3 sums of squares as a matter of default. Well, if you wanted to, you could actually override that by changing the default parameter. So we're going to sort of move on now to ANOVA as a special case of regression, where I will hopefully convince you that everything that we've been looking at in the context of regression and ANOVA and ANCOVA is actually the same thing. Okay? So let's go back to our ANCOVA, but again, let's just ignore the covariate initially. So we looked at how double espresso versus single espresso versus our water drinking manipulation might influence people's gaming ability, and we ended up with a visualization like this, where the three groups seem to be relatively clearly separate from each other. So we can actually code this ANOVA as a linear model, and we're going to use what's known as dummy or treatment coding for the different levels of our experimental factor. So we're going to just code the levels of our factor so that water becomes our default or reference level, which will mean when we build our linear model that the intercept of the line that we're building is going to correspond to the mean of our water group. So we're going to use the mutate function to simply then factor re-level our condition variable so that water becomes the first level of that factor, then double espresso, and then single espresso. And what's actually happening under the hood when we're doing that is R is generating a new sort of coding contrast matrix for our experimental design. And we can ask R to tell us what the contrasts are for our condition variable in our data frame. So this notation here simply means taking our data frame my data, and then the dollar means the condition variable within that data frame. So we can ask for the contrast of our condition variable within our my data frame. And we're told that following this factor re-leveling, our water level of our factor is coded as 0, 0, our double espresso level is 1, 0, and our single espresso level as 0, 1. And to make sense of this, we need to think about it in terms of the equation for the general linear model, the linear model we're wanting to build, where our dependent variable, ability, is equal to the intercept plus a coefficient corresponding to our double espresso group, plus a coefficient corresponding to our single espresso group. And what we're wanting to do when we build our linear model is basically calculate these coefficients. So the intercept, using this coding, we put 0 here and 0 here, which will basically mean that our motor ability is equal to our intercept for our water condition. Our motor ability for our double espresso condition will equal to our intercept plus, basic coding is 1 here, so 1 times our coefficient beta 1 that we need to calculate, plus 0 here, because the coding for our double espresso group has 0 coded here, okay? So this is kind of how we apply our coding scheme in conjunction with the coefficients we're about to calculate to recover the means for each of our 3 experimental groups. So we have ability is equal to our intercept plus beta 1 coefficient multiplied by the coding for our double espresso group plus beta 2 coefficient, and then the equivalent coding for single espresso as well, depending on what level of the factor we're wanting to calculate. So what we need to do is figure out what these different coefficients are. And we do that by building a linear model in exactly the same way that we built a linear model in the context of when we first looked at regression. So in this case, we have ability as predicted by condition. We can ask for the output of this model simply by typing the model name, which I've mapped the output of the LM function onto. And by typing that, we're given the key information that we need. We're given information about the intercept, which is 4.817, which is actually the average for our water group. We're given the information about our beta 1 coefficient, 4.199, and information about our beta 2 coefficient, 1.871. And we can use these coefficients along with our coding scheme to calculate the averages for each of our 3 experimental groups. So let's do that now. So let's work out using our linear model equation what those values actually are. So if you recall, the coding for our double espresso group is 1, 0, so we can plug those into our those contrasts into our equation. So we've got ability is equal to the intercept, which is 4.817, plus beta 1, which is 4.199, gets multiplied by 1, plus beta 2, which is 1.871, which gets multiplied by 0, because what we're wanting to do is work out the double espresso group, so we're using this contrast coding. And if we work out those values, we get 9.016, which is the mean that we calculated earlier of our double espresso group. We can do exactly the same for our single espresso group using the coding for that, which is 0, 1. So we simply put in the contrast coding of 0, 1 for our single espresso group, and that allows us then to calculate the average, the mean, for our single espresso group, which is 6.688. So we have our intercept of 4.817 corresponding to the mean of our water group, and we worked out that the mean of our double espresso group is 9.016 and the mean of our single espresso group is 6.688. So just by building a linear model and by using the appropriate coding scheme, we've basically been able to generate exactly the same means that were generated when we did the ANOVA. And I think this is a really nice illustration of how ANOVA is a special case of regression, and actually, under the hood, it's the general linear model. So we're going to move on to just finish off by looking at ANOVA as a case of regression as well. So we can code ANOVA as a linear model. If you recall from earlier in this video, the adjusted means for the ANOVA are adjusted to take into consideration the influence of the covariate. And those adjusted means of the ANOVA were 7.33 for the water group, 6.32 for the double espresso group, and 6.87 for the single espresso group. So we want to be able to set up a linear model that will allow us to calculate these means. And we do it in a very similar way. This equation up here is very similar to one we just saw a few slides ago, except we've got this additional covariate of gaming frequency now added. Okay, so we're adding this additional gaming frequency covariate, and we build our linear model in a similar way. So ability is predicted by our gaming covariate plus condition. And if we ask for the output of this model, we get the intercept, and then we get the three coefficients down here. So this coefficient here, this is the beta 2 coefficient, this is the beta 3 coefficient. The beta 2 and beta 3 coefficients tell us about the difference between each group mean compared to the reference group, i.e. the intercept, while taking into account the effect of our covariate. Beta 2 is the difference between the double espresso and water group adjusted means, while beta 3 is the difference between the single espresso and water group adjusted means. And we can check that quite straightforwardly by looking at the adjusted means that we got in our ANOVA output. And we see that the difference between the water and double espresso group is indeed 1.01, and the difference between the water and the single espresso group is indeed 0.46. And we can actually work out things a little bit further if we want to. I'm just going to do this for the water group here. We can work out the mean of our reference group, the intercept, by plugging in the values to our equation. So our covariate isn't a factor, so it's not captured by our coding scheme. And we need to enter the mean of this variable, which is 12.62296. So if we enter the mean of this variable alongside the coefficient, in our linear model, we calculate that the mean for our water group is 7.33. So it's the intercept plus the effect of our gaming covariate. Very often in regression, you'll actually scale and center your covariates, which make things a lot easier to interpret. I haven't done it here, but it's something you might want to investigate. So 7.33 is the adjusted mean for our water group, which is what we had when we used the EM means function following the ANOVA. And we can calculate the double espresso and the single espresso group means in exactly the same sort of way. So really just by a way of finishing off here, so you can now build ANOVA models in R for different kinds of designs. You can add between participant covariates, that's what we focused on today. You can sort of factor out the influence of these covariates, and hopefully I've convinced you that ANOVA is indeed a special case of regression. It's just a case of regression with using dummy coding of variables. And actually many statistical models can be built as a variation of the general linear model. And one thing you might be interested in looking at is this resource here by Jonas Lindhoff, which basically talks about how many different common statistical tests and models can actually be reformulated as a special case of the linear model. So if you're interested in really sort of getting into this more widely, I absolutely recommend that you check out this resource. Otherwise, if you'd like to work through the rest of the worksheet now, and it'll give you practice with building analysis of covariance models. It'll also give the opportunity yourselves to discover and hopefully convince yourselves that ANOVA is just a special case of regression.